Hey Phys 1 kids, Campbell here. In this video, we're going to talk about bulbs and circuits, specifically about brightness. Now we're going to talk about incandescent bulbs. Those are bulbs that have filaments that are resistors, and those resistors get hot and they glow. There are other types of bulbs like LED bulbs, fluorescent bulbs. They operate differently. We're going to focus on incandescent. Now, bulb brightness, how bright that bulb is, actually is related to the power output. Remember power, PIV? I times V, or V squared over R, or I squared R? Well, a higher power output means a brighter bulb. And if you think about it, when you buy bulbs, you buy 60-watt bulbs, right? Watt is the unit of power. Now, bulbs that have these ratings of 100 watt or 60 watt or 40 or 25 or whatever, that is based off of a set of conditions. And so this is the thing, when a bulb manufacturer makes a bulb, all right, they say, okay, power, right, PIV, it's based off of the current and the voltage going through the bulb. Now, they can't affect the current or voltage going through the bulb, right? That's all up to you and how your house is wired, if we're talking about bulbs and circuits at home, right? They know that all of your outlets at home should be 120 volts. And if things are connected in parallel to that outlet, then the voltage across the bulb should be 120 volts. So they say, okay, this is the way it should work. So we go to the shelf and pull a filament off that has a resistance that's specific for 120 volts. And they'll use the power is V squared over R equation. And they'll say, okay, for 120 volts, I want a 100-watt bulb. So I need a resistor of blah, blah, blah. Now, if you don't operate your house that way, or say maybe someone wired your house and put things in series, then you're not going to have 120 volts. So you're not going to get that power output. So the power output is based off the design of the bulb, but the only thing the manufacturer can control is the filament they put in it, which is the resistor. So we're going to play a game actually in class called How Bright is Your Bulb? But so just as a lead into that, let's take a look at the resistance for a bulb that the manufacturer makes to be 100 watts for 120 volts. Well, we're going to use this power equation. So we're going to take 120 squared and divide by, right, if we rearrange these, we're going to put the power on the bottom because we're going to solve for R, 100, and we get that it's a 144 ohm resistor. If we do that for a 40-watt bulb, again, 120 squared, this time divided by the power of 40 watts, we get 360 ohms. So, and that makes sense, right? If at a higher power output for a constant voltage, right, you're going to have a smaller resistor, right? Power and resistance are inversely related to voltage. Now, if they're placed in parallel, which is brighter? Well, it would be the 100-watt bulb, right? A 100-watt bulb operated at 100 watts is greater power than a 40-watt bulb. But what if we put them in series? I don't know if you noticed the slide on the front page or the very beginning of this video, but those were in series, and I think the brighter bulb was not the higher wattage bulb or the higher rated wattage bulb. So let's take a look. If we put these in series, that means the current, right? So here's our 120 volts. And we have current going through our 100-watt bulb, we'll call it the 144 resistor bulb. All right, so here's 144 resistor, 360 ohm resistor. And so let's find out, oops, that's 120 volts. Let's find out how much current there would be through this circuit. So if we add up our total resistance, right, our REQ is going to be 144 plus 360, which gives us a total of 504 ohms. So now by Ohm's law, right, the current in the circuit is the voltage in the circuit, the total voltage divided by the REQ. So that gives us a tiny current, 0.24 amps. All right, so now instead, I'm going to use this equation, that power at a bulb is equal to the current through the bulb squared times the resistance of the bulb. So if we take our 0.24 and we square that and we multiply for our 100 watts, so this is for our 100-watt bulb, by 144, what do we get? Wait, that's only 8.2 watts. That's not a 100-watt bulb. That's not going to be a very bright bulb. In fact, that's going to be a pretty dim bulb. What about for the 40 watt? So the power for our 40 watt, again, it's in series, so the current is the same, so 0.24, times the resistor, which is 360. That's a bigger resistor. So 0.24 squared times 360, that's 20.7 watts or 21 watts. Wow, that's still dim compared to 40 watts, but way brighter than the 100 watt. So when bulbs are placed in series, because the rated lower wattage bulbs have a bigger resistor, they actually are brighter. We'll see if you remember that tomorrow when we play How Bright Is Your Bulb? Now, what is the power output in this circuit if the bulb has a resistance of 576 ohms? Pause the video and calculate it. Well, again, you're going to use that 120 squared over the resistor 576, and you should get 25 watts. 25 watt bulb. What happens if we add another bulb in parallel with this bulb? What happens to the brightness of bulb A? Let's go to video and take a look. So here's my light bulb alone. Let's add another bulb in parallel. I want you to observe what happens to the first bulb and how bright the second bulb is. Notice the first bulb brightness didn't change when I added the second bulb. Also notice that the brightness of the second bulb is the same brightness as the first bulb. When I add bulbs in parallel, their brightness doesn't change. I'm just drawing more current out of my power source. So did you notice that nothing happened to bulb A? It's because, remember, in parallel, the voltage across each element is the same, and it's still 120. Now what happens? Well, that just means we're pulling more current out of the whole battery, out of that whole outlet. So the more we put in parallel, the more current we pull out of the battery, but it doesn't affect the brightness of the bulbs themselves. In fact, that's why you have circuit breakers in your home, because if you keep putting things in parallel, you keep pulling more and more current, and there's only so much current that your wires can handle before they get super hot and start fires. So that's the point of that circuit breaker down in your basement or wherever your circuit breakers are. So if you noticed in the video, both of them were equally bright, right? And they were both the same as they were before. And if I add a whole nother bulb in parallel, or another, these are lovely bulbs, aren't they? I'm such a good circuit drawer. They're all going to be identical in brightness, and that brightness never changes. And the only thing we're doing is we're pulling more current out of my power source. But what if we put them in series? If I put them in series, which bulb is brighter? Is it A because it's closer to the positive terminal of the battery? Is it B, or are they the same? In fact, what if we compare one bulb by itself with the battery to two bulbs in series with each other? What do you think? Well, let's go to the video and take a look. Let's hook these bulbs in series and see what happens. Here's bulb A alone. Now let's put it in series with bulb B. Whoa, look how not bright that is. You barely can see the filament glowing. So before, after, in series. Barely see that filament glowing. But they're both equally dim. Now, bulb A was brighter, right? Because it was by itself, so its voltage was the voltage of the battery. But by Kirchhoff's loop law in the second circuit, right, the voltage I gain here, I have to lose here and here before I get back to the battery, which means that the voltage of B plus the voltage of C has to equal the voltage of the battery. So now I have less voltage, right? Less voltage with the same resistor means less power, less bright. In fact, what if we calculate how much power bulb B and C has, right? Before we said that this was a 25 watt bulb. Well, how do we do that? Well, if this is a 120 volt source and these are equal bulbs, right, that means that this is going to be 60 volts and this is going to be 60 volts, right? They're equal resistors, so they're equally splitting the voltage. So if we go that power is V squared over R, then we take 60 squared, because it's split between the two, divide by the resistor, 576, and we get 6.25 watts. Wow, that's not even close to 25. So what do you think happens to this bulb if I close the switch? So I have current that flows out, and currently, with the switch open, right, is flowing through both those bulbs. They're in series and they're identical bulbs. But what happens if I close the switch? If I close the switch, current comes into the junction, and then what happens? Do they stay the same? Do they get dimmer? Does one get dimmer? Does one get brighter? Does one go out? Let's go to tape and see. With the switch open, I have two bulbs that are in series, both dimly lit but equally dim. If I close the switch, which is going to be my alligator clips, look what happens. Whoa, bulb A gets super bright, and bulb B, that filament's not even glowing anymore. So open switch, both glowing. Close switch, bulb B goes out, bulb A stays lit. In fact, it gets a lot brighter. What I just did was I short-circuited bulb B. Well, did you notice A got brighter and B went out? Well, that's because what we're doing is actually called short-circuiting that bulb. We're short-circuiting bulb B because current wants to go where in the path of least resistance, and there is no resistance in our RDL wire, so it's not even going to go to B. It's going straight around from A back to the battery. That's short-circuiting. Now, what do you think about this? These are bulbs. Bulb A and B and C are in combinations. This is a combination circuit. What do you think about the brightness before and after the switch is closed? Again, let's take a look at the path of current. Current flows out of the battery, goes through bulb A and hits a junction. Now, with the switch open, that's really not a junction, right? With the switch open, then these are actually in series with each other, all right? Current just goes straight around. And we already know that those are pretty dim and equally dim, right? But what happens if we close this switch? If we close the switch, we have a junction here. Now current's going to split. And if they're equal bulbs, it splits equally. Well, think about it, and then let's go to tape. So with the switch open, these bulbs are in series with each other. Now I upped the voltage so they'd be super bright so we could actually see this. If I close the switch, notice how bulb A gets super bright, and these guys are dim. You can see that the filament is on. It's very dim, but it's there. So when I close the switch, bulb A gets brighter, bulb B gets dimmer, and bulb C is equally dim to bulb B because they're in parallel with each other. Is that what you thought? Well, what you saw, right, is that A got brighter. Why did A get brighter? Well, A got brighter because when I close the switch, I have a parallel element, and parallel elements have lower REQs, right? So it pulls more current out of the battery. Anytime I put something in parallel in a circuit, regardless of the circuit setup, I'm going to draw more current out of the battery. That means A gets brighter because it has more current going through it now. But B gets dimmer because even though the current went up, it didn't double. So current has to split equally between each of these branches since B and C are equal bulbs. And it's not, so it's less than it was before, so it gets dimmer. And of course, C turns on, but it is equal in dimness or brightness to bulb B. One more, take a look at this. Think about what happens before and after the switch is closed. Pause the video, maybe write some notes in your packet, and then let's take a look. So this is a really messy circuit, but you can see at the top are bulbs A and B, and they are barely lit. All right, the bulb, you can kind of see the filament glowing there, and they're equally dim, and they're in parallel together. But this bulb, our bulb C here, bulb C is super bright. So in my first configuration, bulb C is greater in brightness than A and B, which are equal to each other. This is with that switch open. Now I'm going to close that switch. Whoa, when I close that switch, notice that bulb C got less bright. Let's see, bulb C gets less bright. And bulb A and B got brighter, equally brighter, but definitely brighter. And here we have, and I don't know how easily you can see this, but D and E are equally bright, but they are less bright than all of the other bulbs. So they're in series together in a parallel branch with bulb C. We'll look at this again in class, make it easier to see. Well, if we take a look, what did you see? Well, when we started, right, we had current going through both branches A and B equally, so A and B were equal. It got to the junction here with the switch open, then it just went through C. So that's exactly like the closed switch in our last one. It was just like that. But when we close this switch, now when we have a parallel junction, so we're gonna have to we're putting something in parallel, so we're going to pull more current out of the battery in general, or the power source. So A and B got brighter, but when it hits here, now it's got a split. Now it doesn't split equally, right? Because this is 2 times the resistance compared to just C. So that means that there's going to be more current going through here. So IC is going to be greater than IDE. So with the switch open, C was really bright, and then A was equal to B, and D and E were out. But with the switch closed, C got dimmer, but brighter than A and B still, because it's not equally sharing the current like A and B are. But A is still equal to B, but brighter than they were before because we're pulling more current out of that battery. And now D is equal to E, but they're dimmer because they're in series with C, so they get less current. All right, we're going to do more with bulbs, and we're going to play How Bright Is Your Bulb when I see you in class. So fill out your WSQ, and I'll see you in class.